A new gold rush is beginning, but its treasure lies 240,000 miles away. The key to a future of limitless, clean energy is not hidden on our planet. It is buried in the ancient dust of the moon, in the form of a rare substance called Helium-3. This is not a science fiction fantasy. It is the dawn of a tangible new space age, driven by a high-stakes race to mine this lunar fuel. By the end of this, you will understand how this cosmic quest could solve our greatest energy and environmental challenges, reshaping global power and launching us toward the stars. We will uncover why this isotope is so special and who is already competing to control it. What does it mean for our species to stake a claim on the resources of another world? The secret lies in its atomic architecture. Think of the two main helium isotopes as siblings with a crucial difference. The common one, helium-4, has 2 protons and 2 neutrons in its nucleus. Helium-3, however, has 2 protons but only 1 neutron. That single missing neutron changes everything. When you fuse a helium-3 atom with deuterium, which is a heavy form of hydrogen, something remarkable happens. The reaction releases a tremendous burst of energy, but instead of producing dangerous, long-lasting radioactive neutrons as a byproduct, it creates a charged proton. This is what scientists call anutronic fusion. That charged proton can be directly converted into electricity using magnetic fields, in theory creating a power plant with incredible efficiency and almost no radioactive waste. It is the holy grail of energy science, but this perfect reaction demands a level of heat and pressure that has so far been just out of our reach here on Earth. The fuel itself is also the problem. On our planet, helium-3 is astonishingly rare. It exists in trace amounts, mostly locked away in natural gas deposits or as a byproduct of maintaining nuclear weapons, and there is simply not enough to power a global energy revolution. So we are left with a profound puzzle. If this is the ideal fuel for a clean energy future, why is our own world so poor in it? The answer sends our gaze directly to the silent, gray world orbiting our own. The moon holds the key because it has been collecting this precious substance for billions of years, completely unprotected. Our own protective blanket has become our greatest limitation. Earth's magnetic field is a magnificent shield, a force that deflects the solar wind and protects life from harsh cosmic radiation. Yet in doing so, it also deflects the steady rain of helium-3 particles streaming from the sun. What little does get through is then diluted and lost in our vast, churning atmosphere. The result is a profound deficit. The total estimated inventory of helium-3 on our entire planet is perhaps a few hundred kilograms, trapped in difficult-to-access places like natural gas reserves. For decades, the only practical source has been a byproduct of maintaining nuclear weapons, where tritium decays into helium-3. This makes the fuel not just rare, but wrapped in layers of political and historical complexity. It is a resource born from the machinery of the Cold War, and it could never be the foundation for a peaceful, global energy future. So we are presented with a beautiful and frustrating cosmic irony. The very conditions that allow life to flourish on Earth, our magnetic shield and thick atmosphere, actively prevent us from collecting the fuel that could power our civilization cleanly into the distant future. To solve this puzzle, we must look to a place where those protective conditions simply do not exist. The moon has been gathering this cosmic fuel in utter silence for eons. Without an atmosphere to burn up incoming particles or a magnetic field to deflect them, its surface has served as a perfect passive collector. The solar wind, that constant stream of charged particles from the sun, has bombarded the lunar surface for billions of years. Each particle, including the precious helium-3, slams directly into the fine, dusty soil known as regolith, becoming implanted in the top few centimeters. This process has been most effective in the vast, dark plains we call the lunar maria. These regions, formed by ancient volcanic flows, are rich in the right minerals and have been exposed to the solar wind longer than the rugged highlands, acting as the Moon's natural storage vaults for this resource. The numbers that emerge from this simple, relentless process are almost beyond comprehension. Conservative scientific estimates suggest there could be over 1 million metric tons of helium-3 locked in the lunar regolith. To grasp what that means, consider that just 25 tons of helium-3, fused with deuterium, could theoretically supply the entire annual electrical energy needs of a country the size of the United States. The potential energy contained in that lunar reservoir is orders of magnitude greater than all the oil, coal, and natural gas ever discovered on Earth. It is a promise of abundance that rewrites the very definition of an energy reserve. Yet this treasure is not lying in convenient nuggets or liquid pools. It is dispersed, atom by atom, across millions of square kilometers of barren, abrasive dust. Accessing it will require us to literally process mountains of lunar soil in one of the most hostile environments known. The promise is universe-altering, but the path to extraction is a gauntlet of engineering, logistics, and survival challenges we are only beginning to design solutions for. This promise of cosmic abundance leads us directly to an engineering Everest. To unlock even a single kilogram of helium-3 from the Moon, we must process staggering amounts of lunar soil. The numbers are humbling. Because the isotope is so thinly dispersed, you might need to process 100 million tons of regolith to obtain just 1 ton of the precious fuel. This is not traditional mining. It is more akin to a massive, continuous industrial filtration process conducted in a near-perfect vacuum under relentless cosmic bombardment. The most widely proposed method begins with autonomous, likely solar-powered robotic harvesters. These machines would roam the lunar plains, scooping up the top layer of dust. That soil would then be transported to a processing facility, where it would be heated to incredible temperatures, around 700 degrees Celsius, in a sealed chamber. This step, called pyrolysis, bakes the regolith to release the trapped solar wind gases, including the helium-3. What follows is a complex dance of separation and purification, isolating the tiny fraction of valuable isotope from a mix of other gases. Every single step of this chain, from the abrasive dust that clogs machinery to the brutal temperature, swings between lunar day and night, presents a profound engineering challenge. We are not just building a mine, we are creating an entire, self-sustaining industrial ecosystem that must operate flawlessly for years, or even decades, with almost no human hands to repair a broken seal or unjam a conveyor. The machines we send must be resilient beyond anything we have ever built for Earth. They must be energy efficient because every watt of power is precious. They must be smart enough to troubleshoot their own problems because a radio signal to Earth takes over a second for a simple round trip. Solving these technical puzzles is only the first mountain to climb. For this entire breathtaking endeavor to move from blueprint to reality, it requires a foundation of economics and logistics that does not yet exist. Who will pay for it, and how will they ever see a return? This staggering scale of engineering leads to an equally daunting financial frontier. To even begin processing that lunar regolith, we must first build the entire industrial base from scratch on the Moon's surface. The price tag for such an undertaking is not measured in billions, but in trillions of dollars. It would represent the single largest capital project our species has ever attempted, dwarfing the combined cost of every mega dam, skyscraper, and space program in history. This creates a profound economic paradox, a modern version of the age-old chicken and egg dilemma. Private companies and governments are being asked to invest trillions into a mining operation whose only customer, commercial helium-3 fusion power, does not yet exist. The reactors that could use this fuel are themselves still in laboratories, years or even decades away from proving they can generate more electricity than they consume. So who would take the first, unimaginably expensive step? Would we build the mines to supply a reactor that is not yet real, or would we perfect the reactor first, only to find we have no fuel to run it? This standoff creates a valley of uncertainty that no single entity, not even the wealthiest nation, seems ready to cross alone. For the business case to close, the eventual price of a kilogram of lunar helium-3 must be competitive with every other form of future clean energy, from next-generation solar farms to terrestrial fusion plants that use different, more common fuels. The financial risk is quite literally astronomical, yet the potential payoff is a force that could bend the arc of human history. Success would not just create a new energy company, it would forge an entirely new economic sphere, shifting the center of geopolitical power and offering a permanent, peaceful solution to both our energy needs and our climate challenges. The entities that control this supply chain would hold keys to the future that make today's oil reserves seem quaint by comparison. This reality has not gone unnoticed by the world's leading space powers, setting the stage for a new kind of race where the finish line is not just a flag, but a functioning industrial outpost. This immense financial and technical challenge has transformed the Moon from a scientific destination into a strategic arena. The major space powers are no longer just planning symbolic visits, they are drafting blueprints for sustained industrial presence. The United States, through its Artemis program, aims to establish a long-term lunar outpost. China has outlined an ambitious roadmap for a robotic research station, the International Lunar Research Station, with eventual human habitation. Russia and India have both landed missions on the lunar South Pole, a region rich in water ice and potentially concentrated resources. This is not a repeat of the 20th century space race, which was primarily a contest of national prestige and ideological superiority. The new lunar race is driven by something more foundational: the pursuit of long-term energy security and the economic leverage that would come with controlling the fuel of the future. The ultimate prize is not a flag but a functioning supply chain. This shift from exploration to utilization immediately bumps against a decades-old legal framework. The cornerstone of space law, the 1967 Outer Space Treaty, was written for a different era. It beautifully declares that celestial bodies are the province of all mankind and are not subject to national appropriation. Yet it is strikingly silent on a critical modern question. If a nation or a company cannot own a piece of the Moon, can they own the resources they extract from it? This legal gray area is where theory meets reality. The current interpretation, led by the United States through laws like the 2015 U.S. Commercial Space Launch Competitiveness Act, asserts that while you cannot claim territory, you do own the materials you mine. Other nations are developing their own policies. This sets the stage for potential conflict. What happens if two mining operations target the same scientifically valuable or resource-rich site? Without clear, updated international rules, the Moon could see overlapping claims and disputes that echo the most contentious resource scrambles on Earth. The path forward from this point forks in two very different directions. One leads toward a new era of strategic rivalry, where nations establish de facto economic zones around their outposts, creating a patchwork of lunar territories protected by politics and technology. The other path points to unprecedented cooperation. The immense cost and risk could push nations to form consortia, sharing the astronomical upfront investment in exchange for a guaranteed share of the eventual yield. We might see the creation of a new international body, something akin to a lunar resource authority, tasked with licensing mining sites, ensuring peaceful operations, and perhaps even managing a global helium-3 reserve for the benefit of all nations. This makes modern diplomacy, the art of building frameworks for shared ambition, just as vital as rocket science. The choices made in the coming years will determine whether the Moon becomes a new frontier for collaboration or a new theater for competition. This legal and political uncertainty adds another layer of complexity to an already monumental endeavor, but it also highlights the profound stakes. We are not just deciding how to mine the Moon, we are deciding what kind of future civilization we want to build among the stars. And while nations maneuver, a separate, equally transformative force is gathering momentum in the background, one not bound by treaties or flags. The role of private enterprise is about to change the equation entirely. The legal frameworks may still be debated in Earth's conference rooms, but in the workshops and launch facilities, a different kind of momentum is building. While nations plot their courses, ambitious private companies are entering the arena, driven not by treaties but by visionary entrepreneurs and venture capital. This is a fundamental shift. For decades, space was the exclusive domain of superpowers. Now, firms like SpaceX and Blue Origin, along with a growing constellation of specialized startups, are rewriting the economics of getting there. Their primary achievement has been the relentless drive to reduce the cost of reaching orbit, perfecting reusable rockets that turn a launch from a one-time spectacle into a repeatable, almost routine logistical step. This is not a minor improvement, it is the essential foundation that makes any talk of lunar industry even remotely plausible. If shipping a kilogram of equipment to the Moon costs a fortune, the entire economic case for Helium-3 collapses. These pioneers are solving that first critical equation, but to view these companies merely as cosmic taxi or delivery services is to miss the larger vision. They are deeply invested in the concept of living off the land, a principle known as In-Situ resource utilization. The acronym is ISRU, and it represents a complete philosophical shift for space exploration. Instead of hauling every single drop of water, every breath of air, and every liter of rocket fuel from the deep gravity well of Earth, the goal is to use what you find when you arrive. On the Moon, the most valuable local resource is water ice, locked in permanently shadowed craters at the poles. This ice is not just for drinking, it is a raw material that can be split into hydrogen and oxygen, the basic components of the most powerful chemical rocket fuels. Imagine a future lunar outpost that mines ice, processes it into propellant, and operates a filling station for spacecraft. This turns the Moon from a dead-end destination into a cosmic gas station and hub, enabling cheaper travel deeper into the solar system. The companies working on these technologies are building the toolkit for true economic activity beyond Earth, creating systems that extract, process, and store materials in the most unforgiving environment imaginable. This private sector agility brings a new tempo to the entire endeavor. A government program moves with the careful pace of bureaucracy, balancing scientific goals, political cycles, and international diplomacy. A company, especially one fueled by a founder's obsession and private investment, can move with the urgency of a startup, testing, failing, and iterating at a startling speed. This acceleration could compress the timeline for establishing a functional lunar economy by years or even decades. What emerges is likely to be a powerful, if complex, public-private partnership model. Governments, with their long-term stability and ability to set legal and safety frameworks, would act as the anchor tenants and rule setters. Private companies, with their appetite for risk and innovation, would become the prime contractors and operators, building and running the infrastructure. It is a division of labor that plays to each side's strengths. where public funding de-risks the initial ventures and private efficiency works to make them profitable. This collaboration is already visible in programs like Artemis, where NASA contracts with SpaceX and other firms to deliver cargo and crew. The Lunar Gold Rush, therefore, may not be led by a single nation planting a flag, but by a consortium of international agencies and a fleet of corporate landers, rovers, and processors, all working under a new set of interstellar business plans. This fusion of public purpose and private ambition is creating a new pathway to the stars, one where the very act of going is becoming a sustainable enterprise. Yet, for all this progress in rockets and robotics, the grand promise of Helium-3 still hinges on a machine we have not yet fully built back on Earth, the fusion reactor that can actually use it. But for all the rockets and robotic miners, the entire lunar enterprise rests on a single, unproven machine back on Earth. We have not yet built the engine that can burn this cosmic fuel. The dream of Helium-3 fusion hinges on achieving a reaction that is, by its very nature, far more difficult to ignite than the fusion approaches currently in our laboratories. Today's leading experimental reactors, like the massive donut-shaped tokamaks or the twisted stellarators, are designed for a different fuel mix, deuterium and tritium. This combination is the low-hanging fruit of fusion science. It fuses at relatively lower temperatures and pressures, making it the most accessible path to proving we can generate more energy than we put in, a milestone known as net energy gain. But this convenience comes with a significant trade-off. Deuterium-tritium reactions release most of their energy as high-speed neutrons. These neutrons bombard the reactor's inner walls, making them intensely radioactive over time and converting the entire structure into a complex radioactive waste problem that requires eventual disposal. It is a powerful step forward, but not the clean, anutronic ideal promised by Helium-3. To reach that ideal, we must venture into a much more demanding frontier of physics. Fusing Helium-3 with deuterium requires us to create and confine a plasma, that super-hot soup of charged particles, at temperatures not just hot but staggeringly hot, potentially 10 times hotter than the core of our Sun. At those extremes, containing this raging stellar fire within magnetic cages becomes an epic challenge of stability and materials science. The very magnets needed to hold the plasma must operate flawlessly while being bombarded by the reaction's own energy, and we need materials for the reactor walls that can withstand conditions we have barely begun to simulate. This is why the Lunar Gold Rush timeline is so uncertain. We are racing toward a mine for a resource that requires a lock we have not yet forged. Yet, the promise is so transformative that brilliant minds are not waiting. They are designing entirely new types of reactors from the ground up, specifically for anutronic fuels like Helium-3. Some are exploring compact, self-organizing plasma structures called field-reversed configurations, which could offer a simpler, more stable way to contain the reaction. Others are working on devices that use powerful electric fields to slam ions together, a method known as inertial electrostatic confinement. These are not incremental upgrades to existing tokamaks. They are radical reimaginings of the fusion power plant itself, conceived with the unique properties of Helium-3 in mind. Parallel breakthroughs are making this pursuit more plausible. The development of new high-temperature superconducting materials allows us to create stronger magnetic fields with less energy and in smaller spaces. Advances in laser technology, honed in facilities for inertial confinement fusion, provide new tools to heat and compress fuel with incredible precision. Each of these innovations chips away at the mountain of obstacles, but it is a slow, meticulous climb. A working, electricity-producing prototype reactor optimized for Helium-3 is likely still decades in the future. This reveals the profound scale of the undertaking. We are attempting to solve two of the hardest engineering puzzles ever conceived in parallel. One is an off-world industrial revolution on a dead, airless world. The other is taming a star in a bottle here at home. The distance between a scoop of lunar dust and a glowing power plant on Earth is not just 240,000 miles of space. It is a gulf of scientific discovery and technological maturation that will test our patience, our ingenuity, and our collective will. This long road forces a critical question: is this the only path, or are we placing all our bets on a single, distant star? The immense challenge of building both the mine and the reactor forces a moment of profound reflection. We must ask not only if we can do this, but if we should and how. The central promise of helium-3 fusion is a future free from the environmental burdens of fossil fuels, offering clean, limitless energy without the long-term radioactive waste of nuclear fission. It is a vision of healing our planet's atmosphere and ending our reliance on destructive extraction here on Earth. Yet, achieving that future requires us to begin a new form of extraction somewhere else. This creates a complex ethical and environmental paradox. The moon is not a barren rock waiting for our imprint. It is a pristine historical archive. Its surface, untouched by wind, water, or life, holds an undisturbed record of solar system history spanning over 4 billion years. Every crater, every layer of dust is a page in a cosmic history book. Large-scale industrial mining, with its dust plumes, habitat construction, and traffic, would irrevocably alter that record. Scientists warn that the very processes used to bake helium-3 from the soil could destroy delicate clues about the composition of the ancient solar wind and the bombardment history that shaped the inner planets. We risk erasing scientific truths we have not yet even learned to read, all in the name of progress. This leads to a foundational ethical question: what right do we have to permanently change a celestial body? The moon belongs to no one according to international treaty, but does that grant us a license to transform it? Is the benefit to life on Earth, no matter how noble the goal, a sufficient justification for imposing our industrial will upon another world? These are not technical questions with engineering solutions. They are philosophical ones that require us to define our values as a spacefaring civilization. We must also scrutinize the entire life cycle of this endeavor for its true environmental cost. While the fusion reaction itself may be clean, the path to fuel it is not without impact. The rockets needed to launch thousands of tons of mining equipment and later return the processed helium-3 will burn enormous amounts of propellant, releasing carbon dioxide and other emissions into Earth's upper atmosphere. While the space industry is innovating with greener fuels like liquid methane or even hydrogen, the scale of a lunar mining operation would be unprecedented, creating a carbon footprint that must be honestly subtracted from the clean energy gains. The total sustainability equation only works if the net benefit is overwhelmingly positive over decades of operation. This means we cannot chase this future with the same short-term mentality that has plagued resource extraction on Earth. We have an opportunity and an obligation to do it differently from the start. The framework for this responsibility is only just beginning to be discussed. Concepts like planetary protection, once focused on preventing biological contamination, are expanding to include preservation of scientific value. There is talk of creating lunar heritage sites, areas of supreme scientific importance that would be off limits to industry, much like protected wilderness areas or archaeological preserves on Earth. Mining operations might be required to conduct thorough environmental impact assessments before breaking ground, and to use closed-loop systems that minimize dust pollution and waste. The goal would be to develop a principle of in-situ resource utilization with a conscience, where our technological reach is matched by a commitment to stewardship. This is the deeper challenge woven into the fabric of the Lunar Gold Rush. It asks us to prove that we can advance not just our power, but our wisdom, carrying a new ethical standard with us as we step off our pale blue dot. Given the scale of these intertwined challenges, a functional helium-3 energy economy will not arrive with the suddenness of a flipped switch. This is a story of generations, not years. The journey from today's robotic landers to a steady stream of fusion fuel powering cities is a phased marathon, with each leg building upon the last. The coming decade, the 2030s, will be defined not by mining but by meticulous cosmic cartography. A new wave of robotic prospectors, far more sophisticated than their predecessors, will descend upon the lunar plains. Their mission is to create a detailed resource map, using advanced sensors to measure the exact helium-3 concentration in the soil at different locations. This data is the essential bedrock for all future plans, telling engineers not just where to dig, but where to build an entire industrial operation for maximum yield. If the 2030s are for mapping, the 2040s are for the first foundational steps of industry. This decade could see the establishment of a small, pilot-scale processing plant on the lunar surface, likely robotic and remotely operated. It would be a proof-of-concept facility, designed not for profit but to answer critical questions in the harsh reality of the lunar environment. Can our machines survive the abrasive dust through thousands of operating hours? How efficient is the extraction process when scaled from a lab to a remote outpost? This pilot plant would almost certainly be supported by the first permanent human presence since the Apollo era, a small lunar base acting as a research hub and maintenance center. The goal here is not quantity but quality of knowledge, de-risking the technology one solved problem at a time. The leap from a pilot plant to a full-scale commercial operation is the grandest hurdle. Widespread mining and the first operational helium-3 fusion reactors on Earth are milestones for the 2050s or even the 2060s. This timeline underscores a sobering reality. The children born today will be adults before the first watt of electricity from lunar helium-3 flows into a grid. This protracted schedule exists because every single component of this chain, from the international legal agreements to the reactor's final design, must be invented, tested, and perfected in sequence. There are no shortcuts when you are building a new industrial age on two worlds simultaneously. This entire endeavor balances on a tripod of absolute necessity. The first leg is sustained political will, which must survive across multiple election cycles and geopolitical shifts, treating the project as a multi-generational commitment akin to building a cathedral. The second is continuous technological breakthrough, requiring not just incremental improvements but fundamental leaps in robotics, materials science, and plasma physics. The third, and perhaps most daunting, is the mobilization of capital on a scale rarely seen in human history, invested with the patience to wait decades for a return. Remove any one of these supports and the entire structure risks stalling. Recognizing this phased timeline is crucial. It tempers the hype of immediate breakthroughs, replacing it with a clear-eyed view of the long road ahead. Yet, within that patience lies its own power. Every robotic mission launched, every new superconducting magnet tested, every international dialogue held is a brick placed in the foundation of that future. The transformation is not a distant event. It is a process already in motion, its quiet beginnings taking shape in laboratories and launch facilities today. This gradual accumulation of progress raises a pivotal question for our present moment. With such a long and costly path ahead, what compelling reason do we have to take the first step and the next and the one after that? The true value of this cosmic quest may lie not in the treasure itself, but in the tools we are forced to invent along the way. While Helium-3 is the glittering prize, the drive to mine it will ignite a chain reaction of innovation, creating technologies that reshape our capabilities both in space and back on Earth. Think of it as a grand technological forcing function. To survive and work on the moon, we cannot simply adapt earthly machinery. we must reimagine it from first principles. This pressure will accelerate breakthroughs in fields we barely associate with space today. Autonomous robotics, for instance, will leap forward. The machines that roam the lunar plains cannot be remote-controlled joystick toys. The communication delay is too great. They must become truly intelligent partners capable of navigating treacherous terrain, diagnosing their own mechanical faults, and collaborating with other robots to build structures or repair equipment, all without a single human command. The artificial intelligence and machine vision systems developed for these lunar prospectors will inevitably filter down to Earth, revolutionizing industries like deep-sea mining, disaster response, and precision agriculture, where sending humans is dangerous or impractical. Similarly, the art of construction will be reborn. Building a habitat or a processing plant on the Moon means working in a vacuum, with brutal temperature swings and abrasive, statically charged dust that clings to everything. This will drive the creation of entirely new materials and building techniques, perhaps using 3D printers that sinter lunar soil itself into solid structures or self-assembling modular components. The closed-loop life support systems needed to keep a crew alive for months will push the boundaries of recycling and resource efficiency to an absolute extreme, creating models for sustainable living that could help us manage scarce resources more wisely on our own planet. Even manufacturing will be transformed. In the Moon's low gravity and high vacuum, we can create alloys, crystals, and pharmaceuticals with purities and structures impossible to achieve on Earth, giving rise to a new orbit-based industry for advanced materials. This burgeoning lunar infrastructure, built initially for mining, would naturally unlock other futures. A permanent base with reliable power and life support becomes a destination. The same rockets that deliver mining equipment could one day carry civilian visitors, making space tourism a more substantial and accessible experience. The far side of the Moon, shielded from Earth's radio noise, is an astronomer's dream, offering a perfectly silent platform for telescopes that could peer deeper into the universe's origins than ever before. Perhaps most significantly, the Moon is the ideal stepping stone. Its gravity is only 1/6 of Earth's, making it a far more efficient launch pad for missions deeper into the solar system. A lunar base could manufacture fuel from water ice and service spacecraft, turning the Moon into the cosmic harbor from which humanity sets sail for Mars and the asteroid belt. In this light, the Helium-3 Gold Rush is about much more than energy. It is the catalyst that forces us to develop the complete toolkit for living beyond our home world. The innovation dividends paid by this endeavor will ripple across countless sectors, proving that the greatest treasure we bring back from the Moon may not be a canister of exotic gas, but the collective knowledge of how to thrive among the stars. This realization shifts the entire narrative, framing the lunar challenge not as a distant gamble, but as the next essential chapter in our species' story. But the journey of Helium-3 is only half over once it is purified on the Moon. We then face a delivery problem of cosmic proportions. That precious cargo must travel 384,400 kilometers back to Earth, a voyage through the hard vacuum of space that demands a container unlike any other. Helium-3 becomes a liquid only at temperatures just a few degrees above absolute zero, colder than the void of space itself. This means the shipping vessel is not a simple tank. It is a sophisticated thermos, a cryogenic capsule that must actively refrigerate its contents for the entire multi-day journey, shielding it from even the slightest external heat. The engineering challenge does not end in orbit. This capsule must then survive the fiery plunge through Earth's atmosphere, a violent re-entry that subjects it to searing heat and tremendous forces, all while keeping its super-cold heart perfectly intact. A single failure in this chain, a micrometeoroid puncture or a refrigeration glitch, could mean the loss of a cargo worth billions of dollars and years of effort. This transforms the transportation leg from a simple cargo run into a high-stakes ballet of precision engineering and flawless execution. The cost of developing and operating these specialized return vehicles adds a massive surcharge to every gram of fuel delivered, a financial burden that the entire economic model must bear. To make this back and forth traffic even remotely sustainable, visionaries are looking to break our dependence on Earth for the rocket fuel itself. This is where the Moon's other hidden treasure becomes essential. Water ice mined from permanently shadowed polar craters can be split into hydrogen and oxygen, the very ingredients of the most powerful chemical rocket propellants. Imagine a future where the ships that bring helium-3 to Earth are refueled on the lunar surface using locally produced propellant. This creates a closed-loop logistics system, a true space-based supply chain where the Moon provides both the payload and the fuel to send it home. Such a system would dramatically lower the cost of each return trip, turning a prohibitively expensive one-way delivery into a repeatable, economically sensible shuttle service. Solving this transportation puzzle is the final, critical link in a chain that stretches from lunar dust to terrestrial fusion reactor. Without a reliable, affordable way to bridge that quarter-million-mile gap, Helium-3 remains a fascinating scientific specimen trapped on another world, a solution forever out of reach. The entire venture hinges on this last, daunting step of celestial logistics, transforming a theoretical resource into a tangible commodity that can finally flow into the power grids of our home planet. That final link of transportation brings us face to face with a question of law, not just logistics. Who ultimately owns the fruits of this cosmic labor? The legal framework for this new frontier was drafted in a different age during the tensions of the Cold War. The cornerstone is the Outer Space Treaty of 1967, a document born from a powerful ideal. It declares that space and celestial bodies are the province of all mankind, not subject to national appropriation by claim, use, or occupation. This was a profound statement of shared heritage, designed to prevent the militarization and colonial division of the cosmos. Yet, for all its foresight, the treaty is silent on the very activity now being planned. It does not address whether a private company can own the resources it extracts from a celestial body it cannot own. This silence has created a vast and growing legal gray area, a vacuum that nations are now rushing to fill with their own interpretations. The United States took a decisive step in 2015 with the Commercial Space Launch Competitiveness Act. This law asserts that American citizens and companies engaged in commercial recovery of space resources have the right to possess, own, transport, use, and sell those resources. In essence, you cannot own the Moon, but you can own what you take from it. This was a clarion call to industry, providing the legal certainty needed for massive private investment. Other spacefaring nations are watching closely, and many are expected to enact similar national laws to protect their own commercial interests. This is where the potential for conflict emerges. If multiple nations or companies from different nations all pass laws granting their entities rights to extract resources, what happens when their chosen mining sites overlap? Without a common rulebook, we risk a scenario of conflicting claims and diplomatic disputes played out on the lunar surface, a situation some have termed a scramble for the Moon. The need for a clear, updated international framework is no longer an academic discussion. It is an urgent parallel track to the technological one. The development of this new space governance will be a monumental test of human cooperation. It will require moving beyond the broad principles of the 1960s to craft detailed agreements on how to manage resources, ensure equitable access for developing nations, protect historically significant sites, and establish mechanisms for resolving disputes. Some propose the creation of an international authority, modeled loosely on the International Seabed Authority, which could license mining operations and perhaps even manage a common heritage fund, distributing a portion of the benefits to all nations. Others advocate for a lighter-touch system of coordinated national regulations and transparency measures. The path chosen will fundamentally shape who benefits from the lunar bounty. Will it be a future where access is determined by who has the largest rockets and the most permissive national laws, potentially creating a new form of cosmic inequality? Or can we forge a system that balances the drive for innovation and profit with the original treaty's spirit of shared human destiny? This legal and diplomatic journey is just as critical as the engineering of rockets and reactors. The rules we write now will define the character of our off-world civilization for centuries to come, determining whether the Moon becomes a new chapter in human rivalry or our first successful model for collaborative stewardship beyond Earth. These legal questions will be settled not by astronauts but by algorithms. The success of the entire lunar mining venture will hinge on an invisible workforce of advanced artificial intelligence. This is not about simple automation. It is about creating a self-sustaining, thinking industrial ecosystem on a world where human oversight is a precious and delayed resource. Every link in the chain, from prospecting to processing, will be managed, optimized, and repaired by intelligent systems operating with a degree of autonomy we are only beginning to deploy on Earth. Consider the sheer complexity of the task. A single mining outpost may operate a fleet of dozens or even hundreds of robotic harvesters. These are not remote-controlled toys. A simple radio command from Earth takes over a second to arrive. Each robot must be a self-reliant explorer, capable of navigating the treacherous, dust-choked lunar terrain in real time, avoiding steep crater walls, treacherous boulders, and the fine, abrasive soil that can cripple machinery. Their onboard artificial intelligence will process a constant stream of data from cameras, LiDAR, and ground-penetrating radar, making thousands of micro-decisions per second about where to drive, when to dig, and how to return to base with a full load, all while conserving power and monitoring its own mechanical health. This is a level of machine independence far beyond today's most advanced self-driving cars, operating in an environment with no road signs, no GPS, and no human driver to take over in an emergency. But the role of artificial intelligence begins long before a robot's wheels touch the regolith. It starts in orbit with the cosmic cartography of machine learning. Modern lunar orbiters are already collecting terabytes of data, mapping surface composition, temperature, and topography. Artificial intelligence algorithms will sift through this immense dataset, hunting for subtle patterns invisible to the human eye. They will cross-reference mineral signatures with solar wind exposure models to generate predictive maps, pinpointing not just where Helium-3 might be, but where it is most densely concentrated and easiest to access. This transforms the gamble of mining into a calculated science, allowing engineers to place their first processing plant in the most optimal location, maximizing yield from the very first scoop. Once mining begins, the artificial intelligence's role shifts from prospector to orchestra conductor and chief engineer. The processing facility itself will be a labyrinth of interconnected systems, heating chambers, gas separators, and storage units, all operating in a delicate balance. An AI overseer will constantly monitor thousands of data points, adjusting temperatures, flow rates, and power distribution in real time to maximize efficiency and purity of the extracted Helium-3. More critically, it will perform predictive maintenance. Using machine learning models trained on thousands of hours of simulated operation, the system will anticipate failures before they happen. It might detect a subtle vibration pattern in a conveyor motor that suggests a bearing is wearing out, or a slight pressure drop indicating a seal is beginning to fail. It could then dispatch a repair drone from the outpost's maintenance bay to address the issue, or reroute material flow to keep the plant running while scheduling the repair for the next lunar night. This predictive capability is the difference between a profitable, continuous operation and a catastrophic, months-long shutdown waiting for a spare part from Earth. For any human-tended outpost that supports these robotic miners, artificial intelligence becomes the ultimate life support system and co-pilot. It will manage the intricate ballet of recycling air and water, monitor radiation levels, and control the habitat's power grid, ensuring the safety of the crew with a constant, unblinking vigilance. It would synthesize data from all surface operations, presenting complex situations to human supervisors in clear, actionable terms, and even suggesting optimal solutions. In this symbiotic relationship, humans provide high-level strategy, creativity, and adaptability, while the artificial intelligence handles the relentless, data-intensive execution and system management. This partnership pushes the very definition of a workforce into new territory, where intelligent machines become the essential hands and senses in an environment too hostile, too distant, and too costly for sustained human labor alone. The lunar frontier, therefore, may be the proving ground where artificial intelligence truly comes of age, not as a tool, but as an indispensable partner in building something monumental. This reliance on silicon-based intelligence to harvest a cosmic resource leads us to a final, profound contemplation about what this entire endeavor represents for the human story. The grand narrative of a Helium-3 future is compelling, but it is not the only story being written. History is filled with technologies that seemed inevitable until a simpler, cheaper alternative quietly emerged. The Lunar Gold Rush, for all its promise, faces several potential showstoppers, scenarios that could reroute our ambitions entirely. The most significant threat is not technical failure, but economic obsolescence. What if, by the time we master lunar mining and Helium-3 fusion, the world no longer needs it? The clean energy landscape is evolving at a breathtaking pace. Breakthroughs in next-generation solar panels, which capture more of the sun's spectrum, or in ultra-cheap, grid-scale battery storage that solves the intermittency problem, could provide abundant, decentralized power without ever leaving Earth's atmosphere. Even within the field of fusion itself, the primary competitor is not fossil fuels, but a different fusion fuel cycle. The mainstream scientific effort is overwhelmingly focused on deuterium-tritium fusion. If those reactors achieve commercial viability first, producing abundant power with manageable waste, the unique selling point of Helium-3 becomes far less urgent. The economic case for a trillion-dollar lunar mining operation collapses if a terrestrial alternative can meet our needs for centuries. Beyond economics, the entire endeavor floats on a fragile foundation of sustained political will and public passion. Space programs are perennial targets during budget negotiations. A major economic downturn, a shift in geopolitical priorities toward more immediate Earth-bound conflicts, or simply a generational loss of interest in cosmic exploration could starve the mission of the steady, decades-long funding it requires. Public support, that sense of shared destiny, is the oxygen for such long-term projects. Without it, the political mandate evaporates. Then there is the pure, unyielding difficulty of the science itself. We must be honest about the possibility that the physics of anutronic Helium-3 fusion presents a wall we cannot scale with our current understanding of materials and plasma confinement. The required temperatures and pressures might demand technologies so far beyond our reach that they remain a laboratory curiosity for another century. In this light, the Lunar Gold Rush is not a guaranteed destination, but a high-stakes gamble on a specific technological trajectory. Yet, even if the Helium-3 dream fades, the journey itself will have irrevocably changed our relationship with space. The infrastructure built for that purpose would not simply vanish, it would pivot. the most valuable and immediately useful resource on the Moon is not helium-3, but water ice. A lunar outpost equipped with mining robots, processing plants, and power systems, originally intended for one purpose, could seamlessly shift to harvesting water. This ice, converted into hydrogen and oxygen rocket fuel, would transform the Moon into a cosmic gas station and waypoint. Suddenly, missions to Mars or the asteroid belt become far more feasible, as they can launch from Earth with minimal fuel, refill their tanks in lunar orbit, and journey onward with full propellant loads. The Moon becomes a logistics hub, a port of call in the ocean of space, its value derived not from what it sends back to Earth, but from what it enables us to send elsewhere. This reveals the deeper truth. The future is not a single, narrow path to a predetermined end. It is a landscape of branching possibilities, shaped by our choices, our breakthroughs, and our unforeseen failures. The quest for helium-3 is less about guaranteeing one specific outcome and more about forcing a monumental leap in capability. Whether the ultimate prize is fusion fuel, rocket propellant, or scientific discovery, the act of learning to live and work industrially on another world is the real transformation. It is the process of becoming a multi-planetary species with all the resilience and perspective that entails, so the story may not end with a gleaming reactor powered by lunar dust. It might instead begin with a bustling port on the silent plains, where ships from Earth dock to take on fuel for the next leg of a much longer voyage, their tanks filled with resources harvested from the soil of a world we finally learned to call a workplace. This ultimate promise of helium-3 fusion is a world reborn by energy. Imagine a civilization where the cost of powering a city, propelling a ship, or manufacturing steel is no longer a primary constraint, but a negligible afterthought. This is the societal transformation at the end of the long road. A successful helium-3 economy would not be a simple upgrade. It would be a second industrial revolution, rewriting the fundamental rules of how we live. The most immediate and profound impact would be the near-total decarbonization of our global systems. Transportation, from personal vehicles to cargo ships and aircraft, could shift entirely to electric or hydrogen-based systems, charged by this limitless clean source. Heavy industries like steel and cement production, which currently rely on fossil fuels for intense heat, could run on fusion-powered electric arc furnaces, slashing their massive carbon footprints. Even agriculture, with its energy-intensive fertilizer production and food distribution networks, would be transformed. The very infrastructure of modern life would hum on a foundation of clean, abundant power, offering a tangible, technological path to stabilize our climate and heal our atmosphere. But the benefits extend far beyond simply replacing what we already do. This energy abundance would allow us to tackle problems that today seem intractable due to their colossal power demands. Take the global challenge of freshwater scarcity. Large-scale desalination, turning seawater into drinking water, is an energy-hungry process. With fusion power, coastal cities and arid regions could run massive desalination plants continuously, turning oceans into reliable reservoirs and ending water shortages for millions. Similarly, direct air capture technology, which mechanically scrubs carbon dioxide from the atmosphere, is currently limited by its enormous energy needs. Powered by fusion, these machines could operate at a scale sufficient to actively reduce historical atmospheric carbon levels, not just slow the increase. The energy ceiling that currently caps our ambitions for environmental repair would simply vanish. This shift would ripple through geopolitics, dissolving old tensions and creating new ones. The strategic competitions and conflicts centered on control of oil and gas fields, pipelines, and shipping lanes could gradually lose their urgency. Energy independence would become a universal possibility, not a privilege of geography. The new strategic high ground would no longer be under the sands of a desert, but in the orbits above Earth and on the plains of the Moon. Access to space, ownership of resource extraction technologies, and control of the transportation corridors between worlds would become the new levers of influence and power. This transition would be profoundly disruptive, reshaping entire economies and labor markets. Industries built around fossil fuel extraction would need to evolve or be supported through a managed transition. The economic value would migrate from owning finite resources in the ground to mastering the infinite processes of extraction, conversion, and application. Such a future offers a vision of unprecedented material abundance and environmental stability, a chance to build a truly sustainable global civilization. Yet, this very abundance demands careful stewardship. A world of limitless energy is not automatically a world of equity or wisdom. The same technologies that can desalinate water and capture carbon could also be used in ways that deepen inequalities or create new environmental challenges on a different scale. The management of this transition, ensuring its benefits are broadly shared and its power is directed toward healing and advancement, would be the greatest human project of all. It asks us if we can match our technological genius with the wisdom to build a society worthy of the stars. The vision of a transformed world will only become reality if the public believes in the journey. While engineers calculate trajectories and executives draft business plans, the ultimate fate of the Lunar Gold Rush will be decided in the court of public opinion. This is not a story told solely through technical papers. It is a cultural narrative being shaped by headlines, documentaries, and the conversations we have about our future. How this endeavor is framed will determine whether it receives the decades of sustained support it needs, or whether it is dismissed as a fantastical distraction. The narrative can take many forms, each carrying profound implications. It can be portrayed as the next great chapter of human exploration, a heroic endeavor that unites our species in reaching for the stars and securing a brighter future. This framing taps into our deepest instincts for discovery and progress, inspiring a new generation to look up with wonder. Conversely, the story can be told as one of reckless corporate overreach, where profit-driven entities are given a license to despoil a pristine celestial body for a speculative gain, all while urgent problems on Earth go unsolved. This perspective questions our priorities and challenges the very ethics of expansion. It can also be framed as a dangerous environmental gamble, where we risk permanent damage to a scientific archive of cosmic history for a technology we have not yet perfected. Each of these narratives contains a kernel of truth, and which one gains dominance will shape policy, funding, and the collective will to proceed. Cultivating a balanced, informed public understanding is therefore not a side task, it is a strategic necessity. This requires moving beyond press releases and into genuine engagement. High-quality documentaries that show both the breathtaking promise and the sobering engineering challenges can build a foundation of realistic excitement. Educational programs that bring lunar science and fusion physics into classrooms can spark the curiosity of future problem solvers. Perhaps most importantly, the organizations leading this charge must practice radical transparency. They must communicate openly about setbacks, about the true scale of the environmental and ethical trade-offs, and about the long, uncertain road ahead. A public that feels informed and included is far more likely to grant the patience such a multi-generational project demands. This cultural narrative will do more than influence budgets, it will define legacy. It will determine whether the students of today look back on this era as a time of bold, visionary investment in a shared destiny, or as a period of misallocated ambition when we looked to the sky while our feet were on unstable ground. The story we choose to tell ourselves about the moon is ultimately a story about who we are and what we value most. The race to complete this cosmic supply chain is already underway, with competitors moving at two different speeds. A nation-state operates on the scale of decades and grand strategy, marshalling vast resources toward long-term goals. China's methodical lunar program exemplifies this approach. Its Chang'e missions have systematically mapped the moon, landed rovers, and even brought samples back to Earth, each step building precise capability. Their publicly stated goal is the International Lunar Research Station, a robotic outpost that could evolve into a permanently crewed base, a perfect platform to begin resource assessment and, eventually, extraction trials. This is a marathon run with the steady pace and deep funding of a superpower. In contrast, a private company moves with the urgency of a sprint, driven by market forces and visionary leadership. The commercial partners in NASA's Artemis program, like SpaceX with its Starship vehicle, are not just building rockets, they are designing entire ecosystems for lunar logistics and habitation. Their innovation cycles are measured in months, not years, and they are willing to take bold risks that a government agency cannot. This creates a fascinating dynamic. The first mover could be a nation that methodically builds the entire chain itself, controlling every link from the mining robot to the fusion reactor. Or it could be a consortium where a government provides the legal framework and anchor tenancy, while a nimble company develops the breakthrough extraction technology that makes it all economically viable. The entity that first demonstrates a complete loop, sending even a symbolic amount of processed helium-3 to a prototype reactor on Earth, will achieve something far greater than a technical milestone. They will gain immense strategic leverage. That success would likely set the de facto technical standards for how lunar mining is done, from the types of machinery used to the communication protocols between robots. More importantly, it would establish a powerful precedent in the unresolved legal landscape, effectively shaping the norms of lunar resource ownership through action, not just negotiation. In the nascent market for fusion fuel, this first mover would have an overwhelming head start, securing the initial contracts, attracting the top talent, and building the institutional knowledge that competitors would struggle to match. This high-stakes competition is undeniably driving innovation at a breakneck pace, as each player strives to solve pieces of the puzzle before the other. Yet this very acceleration also tightens the spring of potential tension. Without clear, agreed-upon rules of the road, a scramble for the same strategically valuable real estate, like a crater rim rich in both water ice and solar wind deposits, could lead to disputes. The challenge for our global community is to harness this competitive energy while building robust guardrails for cooperation. Can we create a system where the drive to be first fuels progress for all, rather than creating a new frontier for conflict? The answer will determine whether the Lunar Gold Rush becomes a story of collective human achievement or a new chapter in an old book of rivalry. The true foundation of a lunar economy may not be the glittering prize of Helium-3, but something far more mundane and essential. Water locked away in the perpetual, frozen darkness of polar craters, water ice is the resource that could turn the moon from a destination into a home. This is not a distant dream, it is a confirmed reality. Probes have detected the unmistakable signature of water molecules in these regions that have not seen sunlight for billions of years. The value of this ice cannot be overstated. Through a process called electrolysis, a straightforward application of electricity, water can be split into its core components, hydrogen and oxygen. These are not just the elements of life, they are the fundamental ingredients of the most powerful chemical rocket propellants we use today. A lunar base capable of mining and processing this ice could, in effect, open the first off-world gas station. This changes everything about deep space travel. Instead of launching from Earth with all the fuel needed for a round trip to Mars, a spacecraft could depart with a lighter load, refuel in lunar orbit, and journey onward with full tanks. The moon becomes a strategic port, slashing the cost and complexity of exploring the solar system. But water's role is even more immediate. For a crew living on the lunar surface, it is the ultimate closed-loop resource. It provides drinking water, breathable oxygen, and can even be used to grow food in hydroponic gardens. A reliable water supply transforms a precarious outpost into a sustainable habitat, reducing the need for constant, expensive resupply missions from Earth. This makes the entire venture more resilient and independent. Yet the lunar soil, or regolith, holds other treasures that rarely make headlines. The dark plains of the Maria are surprisingly rich in metals like titanium and iron, deposited by ancient volcanic flows. These are not just simple lumps of ore, they are materials perfectly suited for construction in the lunar environment. Imagine using giant 3D printers, powered by the constant sunlight on the lunar highlands, to sinter this metallic dust into beams, plates, and structural components. We could build radiation-shielded habitats, landing pads, and storage facilities using the very ground beneath our feet, a principle known as in-situ resource utilization. This eliminates the astronomical cost of shipping heavy building materials from Earth. The regolith is also a source of silicon, the key ingredient in solar panels. Factories on the Moon could potentially manufacture their own solar arrays to power mining and processing operations, creating a self-reinforcing cycle of energy production and industrial activity. Even rare Earth elements, crucial for advanced electronics and magnets, are present in the lunar crust. While their concentration might not rival the richest mines on Earth, their location in space could make them valuable for manufacturing specialized components on site, further reducing reliance on our home planet. This multi-resource approach completely reframes the economic logic of a lunar presence. A base established primarily for helium-3 extraction would be a single-purpose, high-risk operation. But a base designed from the start to harvest water, mine metals for construction, and produce its own power becomes a versatile industrial hub. The water operation supports the crew and fuels ships. The metal mining supports construction and expansion. The energy infrastructure powers it all. Within this thriving ecosystem, the helium-3 extraction plant becomes just one department in a much larger, more stable enterprise. The revenue streams multiply. The base could sell propellant to space agencies and private companies. It could offer leasing rights for scientific instruments in its shielded facilities. It could even manufacture and export specialized materials that are easier to make in the Moon's vacuum and low gravity. This diversified portfolio spreads the financial risk and creates a much stronger business case for the massive initial investment. The goal is no longer just to send something back to Earth. It is to build a functional economy where resources are used locally to enable even greater activity. This vision transforms our mental image of the Moon from a silent, dead rock into a bustling frontier workshop, a proving ground for the technologies and economic models we will need to become a truly spacefaring civilization. The quiet plains could one day hum with the activity of a species learning to live off the land, not just on a new continent, but on a new world. The ultimate goal is not a mine, but a new beginning. The pursuit of lunar helium-3 is far more than an energy project. It is the first crucial step in learning how to build a civilization that can thrive beyond the cradle of Earth. The Moon is our training ground, the closest and most forgiving environment where we can master the art of living off the land in a place that wants us gone. Every challenge we solve there, from managing abrasive dust to creating closed-loop life support, is a lesson written directly into our survival manual for Mars and the asteroids. It is where we move from being visitors in space to becoming residents. The energy abundance promised by fusion is the engine for this transformation. With power that is both clean and virtually limitless, our ambitions can expand to a truly cosmic scale. We could sustain large, permanent habitats in the harsh environments of other worlds, providing light, heat, and the energy needed to process local resources into air, water, and building materials. This energy could even power the next great leap, propelling interstellar probes on journeys to nearby stars or sustaining entire ecosystems within generation ships, vessels designed to carry human communities on voyages lasting centuries. These are not fantasies, they are logical extensions of the capabilities we are struggling to build right now. From this vantage point, the immense challenges of the Lunar Gold Rush, the trillion-dollar investments, and the decades of patient science are reframed. They are not obstacles, but the necessary growing pains of a species undergoing a profound transition. We are moving from a single-planet civilization to a multi-world species, and such a change does not come easily or cheaply. It demands a shift in our thinking, from short-term political cycles to generational legacy, from national competition to a deeper understanding of shared human destiny. The lunar outposts and the fusion reactors are merely the tools. The real product is resilience, the accumulated knowledge that allows us to endure and flourish no matter where we go. This long-term perspective turns every robotic lander, every international treaty negotiation, and every breakthrough in plasma physics into a brick in a foundation much larger than any one project. The quiet, gray surface of the moon becomes the anvil upon which we forge our future as explorers and settlers. So when we look at the proposed mines and processing plants, we are not just seeing an industrial operation. We are seeing the blueprint for humanity's first self-sustaining foothold on another world, a prototype for everything that comes after. The Lunar Gold Rush is not the final chapter of our story on Earth. It is the opening sentence of our story among the stars. This immense endeavor stands as a testament to both our ambition and our ingenuity. The Lunar Gold Rush for Helium-3 is not merely a mining venture. It is a grand tapestry woven from threads of cutting-edge physics, Herculean engineering, and deep questions about who we are as a species. It asks us to build industries where none can exist, to govern places no one can own, and to pursue a fuel for a machine we have not yet finished inventing. The sheer scale of this interconnected challenge is perhaps its most defining feature. Every solution creates a new puzzle. Every breakthrough reveals another horizon. Yet within that very complexity lies the engine of our progress. The long and uncertain road from moon dust to fusion power is already transforming us. It is forcing leaps in artificial intelligence, robotics, and material science that will reshape life on Earth long before a single gram of lunar fuel is loaded onto a return vehicle. It is compelling nations to draft new rules for a new frontier, testing our capacity for cooperation beyond our atmosphere. And it is challenging us to look at a barren world and see not just resources, but a responsibility. Whether Helium-3 ultimately becomes the cornerstone of a clean energy future or the quest leads us to other, unforeseen breakthroughs, the journey itself is redefining our destiny. Our future energy security and our identity as a spacefaring civilization are being etched line by line into the dusty plains of the moon. This is no longer speculative fiction, it is the active project of our time. The race is underway, and its outcome will echo through the next century, shaping the world our children and grandchildren will inherit. The story is being written now by the scientists in labs, the engineers at launch pads, and the diplomats at conference tables. But it is also a story that belongs to all of us. What role will we play in this new chapter? Share your perspective in the comments. Subscribe for more explorations of the horizons ahead, and let's keep imagining the future together.